Hello, calculus student. This video is for chapter 3.8, implicit differentiation. So before we go into going through the steps of how to do implicit differentiation, I want to go over the concept of what is implicit differentiation and how does it different from the old differentiation that we have been doing. So first of all, talk about what is mean by the implicit. So implicit differentiation add on implicit equation. Usually when we do differentiation in the past, we have been doing differentiation on function, right? And those are called explicit function, explicit equation. Why? Because the equation from y equal to a formula of x. Because in function form, you would have f of x equal to a formula of x. So this was from f of x. And if we place f of x by y, we have an equation of y equal to a formula of x, such as y equal to x squared, that's the basic one, or y equal to x plus sine x. So these are explicit equation. And then to do a differentiation, so basically we would say dy dx equal to what? Or f prime equal to what? So that would be, I do a derivative of, apply my differentiation rule on the right hand side also and the left hand side. So you see how these matches. I am doing dx because x is the variable that I am doing the derivative on. When we have an implicit equation, the equation are just equation for a graph. They are not necessarily a function. So sometimes I would have equation implicit being xy equal to 1. X and y can be together on both sides, on one side, or I could even have x squared plus y squared equal to 1. This is a circle. These are called implicit equation. Y does not have to be on one side. They could be anywhere. They all mix together. So if I want to do dy dx for this, so say for example, I want to do dy dx for this circle, I would this one. So I would do d dx for x squared. That's no problem because they match. But when I do the d dx on the second term, then I have issue because this variable is y, but I am doing a derivative on x, right? So what we can do is we would rewrite d dx as a fraction, kind of like, change it into a y, and then subtract it, cancel it by doing this. Okay, so just pretend that this can cancel, and then I have d dx, and then y squared. And then we switch the position so that the y and the y here can apply. So it would become d dy y squared, and I would have the dy dx attached to the end as like a variable. So we would do our application of differential for rules here, and then this would be dy dx that attached to the end. So the basic concept is like that. So let's go back to our notes to see how we can go about doing implicit differentiation. So go through the step first, because most of the differentiation of implicit equation would involve steps like this. First, you take derivative of both sides of the equation. Okay, in the explicit form, the left-hand side become dy dx, and the right-hand side would apply differentiation rule. But in this case, we just take derivative on both sides. And if we run into a terms where we would have dy dx as applying on a y term, we rewrite it. So we have d dy instead of d dx, and then we write dy dx at the end. After that, then we rewrite the equation so that all terms containing dy dx are on one side, and all terms that do not contain dy dx are on the other side. Then we factor out dy dx, and then we divide out to solve for dy dx. Okay, so that's the general idea. So let's do a few examples to show. So this is a circle equation, x squared plus y squared equal to 25. I want to find dy dx. So according to what we talk about, the first things we do is to apply derivative dy dx on both sides. So, and then when I say both sides, so that means I apply it to every single term. So I do d dx for x squared, and then I do d dx for y squared, and still equal d dx for 25. Now d dx for x squared, x and x match, so it becomes 2x. This doesn't match, so we have to change it to dy. So it matches the y squared that we want to do, but at the end we would do dy dx, so that eventually this dy and dy cancel, like think of it like that way. And then d dx of 25 is a constant, so this is 0. Now, and then the third step would be we'll do this step. So it'll be 2x plus d dy y squared will be 2y, but I have the dy dx attached at the end equal to 0. So now this term has a dy dx, so it would be on this side. The other term has to go. So we will have 2y dy dx equal to negative 2x, because we will subtract 2x on this side, subtract 2x on this side. And then here I only have one term, so my dy dx I would divide it out, would be negative 2x over 2y. So it's canceling out with negative x over y. So if I am to find the tangent line, so this will give me the formula for tangent line and a point. And notice that I would need to plug in both x and y to get that slope of the tangent line. Second one is a little harder. I think I might need some space. So I'm gonna do d dx on both sides. So be 6x squared plus d dx on is dx, but y cubed, okay, plus 2xy. So this is a product rule, okay, product. So I would be fixing one. So you have to do the FG for also the fake and GIF also, but you can think of it as fake. This is F and this is G, right? So fake would be derivative of F, so it would be 2, and then G, which is just Y, right? Plus GIF. GIF is do the derivative of this, which is dy dx. Oh, it is just a y, so I just should say dy dx times f, which is 2x. So this 2xy become this 2, and equal to d dx of 0 is 0. So this I have to do it by d dy y cubed, but dy dx, because I want to change it so this is y and matches it. So now I am going to do this one, which is 12x, and this would be 3y squared dy dx plus 2x dy dx equal to 0. You see how in this case I have two terms that has dy dx. I factor it. So I would have 3y squared plus 2x on one side, dy dx or dy dx. And this one I would subtract and go to the other side, minus 12x, negative 12x. Now I did divide it out, dy dx would equal to negative 12x over 3y squared plus 2x, and that is the dy dx formula that I can use to find tangent line slope. The third one, oh, I could use this space. The third one we'll do it in class. It's a more difficult one. So let's do one where we actually find the equation of the tangent line. So my equation is x cubed y plus 4y equal to 8. This is a very famous graph. If you graph it, it's a very special graph that is like that. It has a name also. If we have time, we'll go over it in class. So, but anyway, let's do the derivative. So we assign this as f, and we call this g, and you can do f prime is 3x squared. G prime would be just dy dx, right? So let's do a d dx of this. So be d dx of x cubed y, which we would use product rule, plus 4, and because it's just one y, so I would just say dy dx, okay, equal to 0. So this will do product rule, f and g, fig. So that means do the derivative of this one times y. So do the derivative of that one would be 3x squared times y, which is y. Times g, fig would be do a derivative of this. The derivative of y is dy dx times x, which is x cubed, right, time f. And then plus 4 dy dx equal to 0. So again, we minus 3x squared y on both sides. So all the dy dx terms is on one side, all the non-dy dx terms on the other side, and we factor it out. So I would have x cubed plus 4 dy dx equal to negative 3x squared y. So dy dx would equal to negative 3x squared y over x cubed plus 4. So this would give me this tangent line slope. My slope is my x is 2, my y is 1, so it'll be negative 3 times 4 times 1 over 8 plus 4. So let's say, so negative 12 over 12. So equal to negative 1. So the slope is negative 1 for that point. Where's my equation then? My equation will be y minus 1 equal to negative 1, x minus 2. So the equation will be y minus 1 equal to negative x plus 2, because negative 1 times minus 2 is plus 2. So y equal to negative x plus 3 is my tangent line for x cubed y plus 4y equal to 8 at 2, 1.